Today we're going to start our discussion about reaction rates, which is essentially kinetics in chemistry. So we're going to talk about what kinetics mean and what things have to happen in order for a reaction to occur. Okay, so the basis of this section is collision theory. And so what is collision theory? Collision theory indicates that a reaction will only take place when the molecules collide with the proper orientation and sufficient energy. Okay, so that's a lot of words, but we're going to go into detail about what that means. So for our purposes in this chapter, energy is pretty much heat energy. So as temperature goes up, our energy is going to go up. And this should be familiar to you because when we did kinetic molecular theory, an increase in temperature meant an increase in kinetic energy. Okay, so if we don't have enough energy, a reaction isn't going to occur. So for example, baking cookies is a chemical reaction. It doesn't matter how long you let that cookie dough sit on your counter, they're never going to get baked if you don't stick them in the oven and raise the temperature and give the molecules enough energy to react. So in order for a reaction to occur, three things have to happen, and this is the basis of collision theory. The first is really simple. A collision has to happen. So the molecules have to come into contact if we're going to have a reaction occur. They can't react if they're not in the same space and if they're not touching each other. The second thing that has to happen is that they have to be in the correct orientation. So sometimes they can bump into each other, but if it's not in the right orientation, the bonds can't break and reform in a different way. And then the third thing, which I already alluded to, is that they have to have enough energy for the bonds in the reactants to break so that the reaction can occur. So we're going to go into a little bit more detail about each of these things. So the first is the collision has to take place, okay? So here we have a reaction with N2 and O2, and they have to come together in order to react, all right? If when they come together, they don't have enough energy, so that energy is represented by this burst here, so you can see there's a really big burst here and a really small one here. So if they don't have enough energy, they're just going to bounce back and you're still going to be left with N2 and O2 at the end, and no reaction will occur. Okay, you can see here that in order for these two things to react, the two nitrogens have to be lined up with the two oxygens so that you can change the bonding to be this direction. Okay, so if they were to collide in this orientation, that's not going to result in a reaction because this nitrogen and this oxygen aren't touching each other, and so they can't react. Okay, so to get at this, we need to look at something called activation energy. So the activation energy is the minimum amount of energy that's required to break the bonds between the atoms in the reactants. Okay, so we've already talked a little bit about endothermic and exothermic reactions. So what is shown here, the reactants have less energy than the products, okay, but we don't just need enough energy to get from here to here. We also need enough energy to get up here, okay? So if you remember, breaking bonds requires energy. And you'll get some of that energy back when you reform bonds, but you have to get up high enough to break the bonds, and then you'll get some of that energy back when you reform the bonds in the products. So the energy, activation energy on this graph is represented by this distance here between the energy of the reactants and the energy of what we call the transition state. So that is the least stable state along the reaction pathway. Okay, so now I've talked a little bit, alluded to this rate of reaction. So what actually is the rate of reaction? So the rate of reaction tells us how quickly the reaction happens, but we measure it based on the amount of reactant used up in a particular amount of time. So we can calculate the rate of reaction using the change of concentration of reactant or product divided by the change in time. So let's take a look at an example using pizza. So if we start off with a whole pizza at 0 minutes, let's say it has 8 slices, excuse my drawing. Okay, so we have a pizza that has 8 slices at time equals 0. Okay, if we wait 8 minutes and we come back, we can find that the pizza is now half gone. So if we call this t equals 8, then that is how much pizza has disappeared in a particular amount of time. Okay? And then if we come back 4 minutes later, so this will be after 12 minutes, what we find is that we only have 2 slices of pizza left. Okay? And so, and then if we come back again at 16 minutes, what we have is no pizza left. Okay? So using this example, we can calculate the rate of pizza disappearance. Okay? So if we go from t equals 0 to t equals 8, our change in time is going to be 8 minutes, and our change in pizza is going to be 4 slices. So 4 slices have been consumed from time 0 to time 8. So if we do 4 divided by 8, that's a rate of a half a slice per each minute. Okay, and then we could also do this from 8 to 12. So that's a change in time of 4 minutes. So that was what would go on the bottom. And we've actually lost 2 slices. So 2 divided by 4, again, half a slice per minute. And you can see that that rate should be constant throughout, just independent of how much time has passed or how many slices are eaten. The ratio between the two should remain constant. Okay, so what are the factors that affect the rate of the reaction? So I mentioned temperature already, and that's because temperature is related to kinetic energy. So the faster the molecules are going when they collide, the more energy there's going to be to break those bonds. Okay? And then concentration is also a factor. So the reason this is a factor is because the more molecules you have in a given space, the higher their concentration would be, and the more likely they are to collide. So if I have 2 of you walking around my classroom blindfolded, you might eventually run into each other. But if I had 20 of you walking around my classroom blindfolded, you're pretty likely to run into each other because there's so many of you and so many other people that you could run into. So depending on what kind of substance we have, that concentration can be expressed differently. So molarity, which we just covered, is how we would talk about the concentration in a liquid, right? That's going to be the number of moles per liter. In a gas, we could talk about the number of moles in a given volume, but usually we refer to pressure as our concentration. So the higher the pressure is, the more molecules there are in a given space. Okay? And then surface area applies to solids. So a solid doesn't have a concentration because it always takes up the same amount of volume because the density is the same. But if we make more of the surface of the solid available to interact with either molecules in a solution or in a gas that are going to react with it, then it will react faster. So what this means is if you grind up your solid, it will react faster than if you just put it in as a solid block because there's a lot more of the surface exposed to be able to collide with other molecules. Okay, and then the last thing that affects the rate is a catalyst. So catalysts speed up the reaction by providing an alternative pathway for it to happen. So what this would look like is if we have the reaction that we just had on the previous slide, if this is the normal reaction, all right, and remember the height of that hump is our activation energy, a catalyst might provide a curve that looks like this. All right, and you probably talked about catalysts in biology. Catalysts do not participate, are not used up in the reaction, but they do participate by changing the reaction pathway. And we'll talk about this a little bit more in class, and if you take AP, we'll go into a little bit more depth about it. But generally, the catalysts students are most familiar with are enzymes. So we'll take a look at how that works. And the one you've used in class is when we did the reaction lab with hydrogen peroxide. We stuck a chunk of potato in there, which has an enzyme in it called catalase, and that acts as a catalyst to break down that hydrogen peroxide. All right, so that wraps up our discussion of reaction rate, and we're going to talk about this a little bit more in class in the next few days.